Talk about the principal quantum numbers. There are 4 principal quantum numbers. I'm going to try to display how these quantum numbers relate to the average relative distance the electron is from the nucleus, the shape of the path that electron takes, the direction it takes, and the spin. These are colloquialisms or easy speaks for the 4 principal quantum numbers. So that last one, their spin. I also want to show how it's related to the periodic table. Chemists are interested in electrons, and the periodic table is designed around how Mother Nature arranges the electrons around the nucleus and we use these 4 terms to describe the location of the electron with respect to other electrons and to the nucleus. So the first principal quantum number is 1, 2, 3, 4. Okay? And those principal quantum, now for the sake of Gen Chem, those principal quantum numbers relate to the average relative distance the electron is from the nucleus. So an electron that is in the first quantum shell or the second quantum shell or the third, it's getting farther away from the nucleus, the higher the first principal quantum number gets here. And this describes the average relative distance. So layers of an onion is an analogy here that's really good because that gives the 3-dimensional nature to the electron's relative distance from the nucleus. Russian nesting dolls is also very good because, the nesting doll, there's a doll inside of a doll, inside of a doll, inside of a doll. Those are good kind of visuals there as well. And also, I've labeled the vertical axis here because when an electron is in this box, when an electron is in this box versus this box versus this box, we are trying to represent an electron that is farther away from the nucleus. Now for Gen Chem and most chemistry purposes, we really just use the first 2, really just use the first 4 quantum numbers right there. I'm just going to do the first 2 because it's only where things get interesting. So the shape of the path. In the first shell right there, the shape of the path can only take on one shape, and being the closest to the nucleus, and that shape of the path is an s orbital. It has a principal quantum number value of 0. That 0 equates to an s orbital, and that s orbital is a spherical orbital. I'm trying to put a little window reflection on there to give it 3D nature right here. The nucleus is invisible in this picture, but I'm going to put a dot right there just to represent the nucleus. And those are where the electrons can survive in this first orbital right here. And I'm purposely pointing at this first row. Now, the direction of the s orbital, it doesn't have a direction. It is universal in every direction, the x, the y, and the z, because it's a sphere. So there's no directional element to describe the shape of this path. Now, the spin of the electrons. Electrons can be thought of as point charges that spin either clockwise or counterclockwise. And when a charged object is spinning, it creates a magnetic field. So when electrons become close enough in proximity to one another, occupying the same orbital, there's a measurable spin quantity. And it either has a value of +1/2 or -1/2, a spin up, spin down. And we draw that with these arrows, a spin up and a spin down. You get real picky, it's important to use just half the arrowhead because we're trying to represent one electron with the spin up, one electron with the spin down. If you get into OChem, if it's a double-headed arrow, that's talking about 2 electrons. So on our periodic table here, 1 electron per box. There are in the closest relative distance shell of an electron, of an atom, that electron has a spherical shape to its path, and only those electrons can fit in there. In the second shell, there are 2 types of orbitals, or 2 shapes of path that can occur in the second shell right here. The first one is an S. So there is a 0. We call that an S right there, and that has the spherical shape to it. And let me redraw this right here, okay? Notice the difference between these two. The 1s orbital has a smaller or shorter relative distance to the nucleus. Here is the nucleus in the middle of the 2s orbital. To make my picture accurate, this must be a larger orbital because it is a farther average relative distance from the nucleus. This orbital, s orbital, has no direction to it. Excuse me, it has universal direction in all directions right here, and it can take on, and it has electrons of a spin up and spin down. Only 2 electrons can fit in here. So this right here, this box will be better off kind of over here. So let me do that. But these 2 columns here represent electrons that can fill into the s orbital. We have a vertical and a horizontal component to how electrons fit into the periodic table. In the second shell, the periodic table has 6 more boxes present. Because we're a little further away from the nucleus, there's a larger perimeter or surface, so more electrons can arrange themselves in the second shell of an atom. These electrons have a different shape to their path, and they have a different direction. They have, these are called p orbitals, and they have 3, and I'm going to draw a generic p orbital right there. And there are directions to these p orbitals. These orbitals, these p orbitals, they have kind of a linear geometry. They're like 2 balloons tied together, and they can take on an orientation or a direction along the x, the y, and the z-axis. This is the z-axis meant to be coming out of the board towards you. The orbital that is on the x-axis, let's say, looks like that. Where's the nucleus? Right there in the center, at the origin. This is the px. The orbital that is on the y-axis, this is the py. They are overlaying each other. Okay? So I have to draw 3 of these to correspond to each axis of 3 dimensions. And then there is a pz, and it's hidden in here. The pz has the same shape. P orbitals have the same shape, but there's a p orbital coming up and down called the pz. These orbitals can take on electrons that match the spin configuration as well, and one up and one down. So this one, to kind of recap, this 1s orbital has 2 electrons, a spin up, spin down, a 2s2 orbital, 2s, 2 electrons, has a spin up, spin down. And then this 2p can fit 6 electrons. There are 3 orbitals, px, py, pz. There's a lot of information in this talk right here. The main takeaways I would like for you to try to soak into is how the periodic table is guiding you, how Mother Nature arranges the electrons around the nucleus. She can show you the average relative distance and the shape of the path that those electrons take on just by counting right here. This picture here tries to show your atomic vision of how those shapes of those paths changes. As we get further from the nucleus, things get larger and larger. Makes sense. The p orbitals require a little bit of mental gymnastics, trying to imagine these 3 p orbitals laid on top of each other. I didn't even try to draw these guys in here. There's some 3D modeling programs that do that a lot better. Hope this helps. Thank you.